So I think we left with this slide. There's all sorts of different forces. There's a force of friction, there's a push force, a pull force, there's the force of the wind. There's actually an EMF, electromotive force, where electrons are flowing, having a positive force with them. But this is the force of gravity. So who came up with, oh, it's on the slide. Newton came up with the force of gravity, which actually is my maiden name. How cool is that, right? Anyway, so he worked out the details. A lot of times we do this in science where we're like, okay, we know this force of gravity, which actually we call weight to a certain extent, is a pull for us to our mass towards the mass of the Earth, center of the Earth actually. And it's related to how massive the two objects are. So this actually, in outer space, I like to think of outer space, you can actually have two objects that would be attracted to each other with similar masses. The force they feel towards each other would be related to their mass. G is a constant, and R, we square that. That's the distance between the two objects. Okay. So actually, I mentioned that the force of gravity is what we kind of call weight. Weight and mass are not the same thing, even though we all kind of use them interchangeably. Weight is a function of the masses that are being pulled towards each other times the gravitational law constant, capital G, divided by the distance that's between them, squared. Okay, so that's actually what weight is. Forces, the force of gravity, and all forces actually are expressed in units of newtons. I guess that's coming up. So here we go. Here's the two masses that go in that equation are right here. So this mass would go here, and this mass would go here. I'm telling you, the mass of the Earth is a lot bigger than the mass of any object on the Earth, obviously. But what happens if you start to cut the distance? How do I say this? What happens to the force of gravity is the two objects that are having that force get closer together. Is it stronger or weaker? It gets stronger, exactly. So one of the things we're going to talk about in astronomy is the concept of a black hole. So the deal with a black hole is basically it's taken matter and squished it down, squished it down, squished it down. Okay? And I kind of liken it to if you take Christmas time when we have little kids around, wrap everything. I don't know why we wrap everything, but they tear off all the wrapping, and then you're like, okay, now what do I do with it? Well, you stuff it in a trash bag. And to get more in the trash bag, you stuff it. Okay, now there comes a time when you can't stamp it down anymore. Think of like a black hole as basically that stomping on steroids, where you take all that mass and it doesn't seem like you can stomp it anymore, and you do. My point's going to be that if you were to, I know it doesn't work this way, but if you were in outer space and had, all the wrapping paper that's ever been made, and you stomped it into a bag, made it really, really small, you can actually make a black hole out of it. You can make a black hole of wrapping paper. How strange. But you can make a black hole out of anything. And the thing is when you step on it, in that case, you would actually, if you were stepping on it, you would be really close. That R is very small. And you guys told me when R gets smaller, the force of gravity gets larger. So that's kind of what we have going on here. We can make the Earth into a black hole. I don't suggest it. I think I've heard if you take the mass of the Earth, it'd have to be like maybe the size of a golf ball, maybe. Then you've got a black hole. So anyway, yep. So this distance is relatively constant. So the W means weight. Okay, weight can be expressed this way, which this is pretty cumbersome, right? Oh my goodness gracious. Weight also is actually, I'm going to introduce G, and little g is the acceleration due to gravity. So another way to say what weight is, it's much easier. Weight is the mass of the object times what we call the acceleration due to gravity. Acceleration due to gravity. I can never spell acceleration. Oh my gosh, thank goodness for spell check. Thank goodness I went into a field where I don't have to worry about spelling. So I think I mentioned this the other day. Here we have, not drawn to scale, right? Here we have a happy astronaut on the Earth and a happy astronaut on the moon. How does the mass change as the astronaut, it's on the slide, as the astronaut goes from the Earth to the moon? How does the mass change? It doesn't. The mass does not change. How does the weight change as he goes from the Earth to the moon? It gets lighter. So the weight changes just because this term right here is getting less. Yep, exactly. So this last one is kind of like the whole outer space. You know, I can't imagine that we can take any two objects while we're standing on Earth and say, hey, these two objects have a gravitational force attracting them, right? Well, I think, and because actually the force of gravity that they feel towards the Earth is so much bigger than what but they do. They really do. But sometimes I have it as a test question. I don't know here, but in general, I'll put the fraction 1/6. In general, 1/6. You basically, and I'll call this 1, let's see, I'll call this 1W as in weight, and I'll call this 1/6 W as in weight. Then we could do the math. What if you take 162.2 newtons divided by 980 newtons? Calculate for 3 calculations. You get about 1/6. Yep, about 1/6. So it's a lot. Okay, so now these will be due on Monday. Sorry, I gotta give you a minute to write it down, don't I? So, page 76, sometimes I'll put SA for short answer. Page 176, short answer number 4. And then page 79, and it's problem number 2. And for 79, problem number 2, I make a note here. We're going for net forces. Net forces means kind of forces. You look at all the forces acting together and come up with what we call the resultant, or kind of who's going to win. That's tug of war. Net forces is tug of war. And then also problem number 6. So problem number 2 and problem number 6. And my hint for problem number 6 is to use F is equal to ma. Does anybody remember which of Newton's 3 laws F is equal to ma is? First, second, third. Fingers, what do you think? First, second, third. Don't know. Third, second. I think it's the second. I know it's like. I know my slides are misleading. It's the second. Okay. Very good. We can get through this. Come on. This is so cool. Actually, this is why I brought my little science bag with some goodies. And I'm going to try to convince you kind of this idea of as things fall, free fall, okay, they all get faster and faster and faster, fall faster and faster and faster, which maybe the word is, if something falls faster and faster and faster, we use accelerate. They accelerate at the same rate, okay? So actually, this is Galileo, and this is an exaggerated leaning tower of Pisa. Isn't that so cool? And what they're showing is Galileo has 2 rocks, okay, and let's say they made the same thing. Which rock, the left or the right one, weighs more? It looks like, to me, that looks like the bill a little bigger, so I bet that weighs more, okay? The W is bigger, the M is bigger, right? But what he found out actually is that the person down here at the bottom, I don't know how he did this, but anyway, the person down here at the bottom saw them hit the ground at the same time. Now this is almost like this is what they call a misconception. There's misconceptions and everything. Misconception just means the public thinks it's one way, but it's really another way. So this misconception is that it seems like the bigger one would hit the ground first. And Most people would say that. But they're being accelerated due to the force of gravity, and that force of gravity is constant on both objects. All right, well, that makes me dizzy. So there's a lot of what we call constants in science, physical science. There was the gravitational law constant. You don't have to memorize that. You do have to memorize this G. Okay, so you will want to memorize this. In general, for every 1 second, I'm going to throw something down, and for every 1 second you let something fall, it's going to go 9.8 meters per second faster than it was before. So if it starts at 0, it falls 1 second, it's going to be at 9.8. You let it fall second, and it's 9.8 plus 9.8. You let it fall third second, and it's 3 times 9.8. Really? That's how it goes. And so here is I'll do my slide, and I'll do my little demo, and then I'll do a video. So here is actually a figure. Now, if I were to take a feather, I couldn't find any feathers in the lab. I don't know what that says. But so if I were to take a feather and a penny, honestly, I'd stand up here, and which one would take the longest to fall? Feather book. And that's true. And it's like, well, Mrs. Snipes, you just said that it's like the mass doesn't matter. Well, what's doing the whole feather thing is aerodynamics. Okay, feathers were meant to fly. Okay. So what you're seeing here is if we remove the air particles, then that feather can't float down. So this is just a bell jar that's sealed up, and what we do is pull a vacuum on it, so we remove all the air particles. Okay. Then at the top, you release the feather and the coin, and there's no air. Okay, so they both fall. Isn't that cool? I just love that. So anyway, I tried to think in my office or whatever if I could come up with some objects that would have similar aerodynamics. I could pass these around, but just trust me, this is a little bit heavier. So I was in my office doing this a little bit. What are you talking about? So we don't have like a thing down there to capture it, but they're similar. Okay, so similar aerodynamics. So I haven't tried this one yet. So these are definitely wow. Okay. So which one's heavy? These are easy. So this is heavy. These are rice, and this has aerodynamics. But our thermodynamics, our aerodynamics are all the same. Let's drop these, and I was like, oh my gosh, custodians are gonna kill me if they like bust open. Oh well. Oh, you only live once. Okay, so here we go. I'm liking it. I'm liking it. All right. All right. I'm supposed to bring munitions to school, people. Okay. Not bad. A little messy. It could have been worse. Okay. Did they look like they hit at the same time? Next time, use a little tape. Okay. That's close enough. We'll make everybody wonder. So I am going to show you a video, and it's a famous video. I'm not going to put this in the form of a question because I might embarrass people. I will just state that there are some people who don't think we went to the moon. I'm not going to ask if you thought we went to the moon. I really think we went to the moon. I know we went to the moon, but some people don't think we went to the moon. And if you think we didn't go to the moon, then this is going to be a hard one to watch. But one of the things on the moon that they did
was to, well, I'll just show you.
Oh, there's a little trio there.
All right. So weight you can think of as being calculated this way, which is really complicated. Alternatively, we can go with weight is simply this right here. The weight of an object is equal to what its mass is times the, on Earth, that would be the 9.8 meters per second squared. That's what that little g is. Okay? All right. So we're kind of building up to working some problems. This is what I described a little bit ago. So this dude is dropping, hopefully it's nice and soft, bouncy ball off the top of the roof. At time is equal to 0, its velocity is equal to 0. What will its velocity be after 1 second? 9.8 meters per second. Exactly. 9.8 meters per second. And we're going to actually do some distance calculations, but this is its velocity, and actually this is going to be the length that it has fallen. So I'm going to put the second up here. So how fast will it be going at the second? So, right, 19.6 meters per second, exactly. But notice that the length here, just because it's going faster, and these aren't drawn to scale, are they? Because here we have 4.90 meters, and here we have, I mean, it almost looks like twice that, but really it's a lot more than twice that. Does that seem right to you? Okay, like this, if this is about 5, this is about 20. Okay, and so like they aren't doing their picture justice. It should look more like, and there's some really cool, maybe I'll try to get one for Monday, some really cool photography out there that is done that where it's the same sort of scenario where you're throwing something off of a building or something. It's here, and then it's here, and then it's here, and then it's down here. So each second it falls is going up. And this image doesn't do that. But shame on them. I guess I ran out of paper out of it. But that's right, it's going twice as fast. What about the third second? Have to get a calculator, yeah. 29.4. Is it on the slides? Okay. So if you take 3 times 9.8, you get 29.4. Exactly. Et cetera, et cetera. But like I said, shame on them. They don't give the distance like they should. That's okay. Cool. Well, like I said, we're kind of gearing up to be able to do some problems. One of the things I think is missing on this slide is, do you remember the other day, what Greek letter does this represent? Change in. Yep. That means change in, and the Greek letter is delta. Yep. Delta change in. Perfect. So actually we could rewrite this, and I think I did the other day. What does the bar mean over the A? Average. Perfect. Average acceleration. We could just go change in velocity divided by, instead of time, I usually put change in time. Cool. So does this make sense that this actually up here, the little g, we're always going to go with, in this class, 9.8 meters per second squared. That is an acceleration due to gravity. I can't spell acceleration. Oh my gosh. I don't think it's 2 C's. I can't remember. That's a G due to gravity. What's that? Oh. All right. I'll work on it. So here we go. Acceleration. Now it doesn't have to be acceleration due to gravity because, oh my gosh, we definitely have acceleration due to like our cars, our little acceleration thing. We can have accelerations due to things other than just gravity. But whatever your acceleration is, you can calculate it by taking the final velocity and subtracting the initial velocity. I think we did some of these the other day. and dividing by the time over which it occurs. Well, this is a new one, and this actually will be on, I'll double check what your, remember I told you you're going to have an equation sheet on this test. I will double check what that looks like. But your final velocity, how fast it's going to go in the end, is equal to what you start at, your initial velocity, plus whatever acceleration it's experiencing times the time that you're going to go ahead and let it experience it. It's true, it works out, and it kind of makes sense, I think. It should make sense. Now, there are special cases. If your initial velocity is 0, by this, if you're starting at rest, basically, what they say, if that's 0, you're starting at rest, can you see where this equation becomes this equation? That's all that's saying. Just a special case. Well, let's do one, shall we? And we're gonna keep dropping things. Well, I wouldn't suggest dropping without taping it first, something like this. Actually, this could have shattered too. That would have been really bad. I would have had to install class for the day, I think. Okay, so we're gonna drop something. So I told you, remember when I work a problem like this, a lot of times I'll draw a little picture. So here's my little picture. I won't make it a leaning tower, but that's my little tower, I guess. An object is dropped from the side of the building. Okay, it doesn't say what the object is because remember, it doesn't really matter. We're going to assume that aerodynamics are not playing. I'll just make it a ball. Object is dropped from the side of the building. Okay, how fast is it falling due to gravity after 5.2 seconds? So I'm going to let it fall. And I'll go ahead and put T, or delta T is equal to 5.2 seconds. And honestly, you guys can already look at kind of the previous slide, and you know it's going to be falling faster than that, even 4 seconds. Does that make sense? So to knock this out, what we're going to do is we're going to use this equation right here. We can use this equation because the initial velocity, v sub I, is equal to 0. How do I know that? Because it's in the problem. We dropped it out of the building. Didn't say we shot it out of the building. Interesting. And then let's see, an object's dropped from the side of the building. How fast is it falling? So down here, v sub f, I'm going to put question mark is equal to question mark. So that's sort of what we got going on. I guess one more thing, and I haven't usually, but it makes sense. In this little problem, I'm going to go ahead and say one of the things I know is that I know it's going to accelerate, I'll put A, at 9.8 meters per second squared. Does that make sense? I'm going to use as my A actually G. Now let's go ahead and go back up here. So now we've come to the point where, to me, it feels like plug and chug. So plug and chug means that you have an equation ready to plop in. So notice we're after the final velocity, which is already isolated, what we say isolated over here on the left-hand side. We have acceleration and we have time. Now, on your test and on your homework, one of the things I'm going to ask you to do is make sure you carry your units with you. So it looks like this. V sub f is equal to acceleration. So I'm going to go ahead and put the acceleration like this, 9.8 meters over seconds squared. I know I put meters per second squared here, but I want to go ahead and show those seconds squared in the bottom. And I'm going to put parentheses around that, and then I'm going to go grab my time. So my time was 5.2 seconds. I'm going to put 5.2 s over 1. And the reason I'm kind of being careful about my units like that is so now, like we looked at before, my units cancel. So this 1 second cancels just one of these. So I can make one of these go away. And I'm left with 1. So I'm going to change that 2 to 1. So in working physical science problems, I'm all about looking at the units. So, grab my calculator, type in 9.8 times 5.2. So what do you think? Like, how many digits do I have here? How many digits do I have here? Yeah. So I'm going to read this number from left to right and only keep 2 digits. So a lot of times I write I'll write CALC, so that's what my calculator displays. My calculator displays 50.96. Okay, and then I write NANS for what answer I'm going to go with. And I told you I'm going to keep 2 because you told me 2 and 2, so I'm going to keep 2. So I'm going to keep this one. I'm going to keep the digit in the tens place, the digit in the ones place, but I'm going to stop there. So do I leave that as a 0 or round it up to 1? So 51. So what would my units be? Yep, 51 meters per second, exactly. And so if you've worked a problem like this, hopefully you're like, the units of that you get in the final make sense with velocity. It's like, yay, go eat chocolate, or something. All right, let's do another one. Do you guys have this slide? No? Oh, try it. You have this slide? No, you don't. You do have this one? Yeah. But you don't have this one? Okay. Well, just bear with me and put this in your notes somewhere. All right. So this one says, and I'll draw a picture so then you can just draw the picture because a picture's worth 1,000 words. And who wants to do words when you can do pictures? There's my building. Okay. And it says we're going to drop it. We'll make it a ball. How many seconds will it take before it's dropping at a rate of 120 meters per second? So V sub I, what's the initial velocity? It is 0. 0 meters per second. Okay, down here, I'm going to show it down here, and my final velocity, according to the problem, is going to be 120 meters per second. Cool. And now, here in my diagram, I'm going to put question mark D for distance. Wait, sorry. Thank you. Thank you. Question mark T for time. I was like, there's no D up there. Perfect. Thank you. So I'm going to put T is equal to question mark. That's better. Cool. Good deal. So what is my A? Perfect. Yep, 9.8 meters per second squared. Yep, yep. So now this is a deal where I'm not ready to plug and chug. So one of the things I'm hoping, and I mentioned this the other day, is that you can do a little bit of algebra or let me know how that works for you. But what I want to do, since I'm after time, is get time, we'll say, by itself. So how can I do that? Get rid of A. Exactly. Get rid of A by dividing both sides by A. That's how we do it. Again, I'm not a math teacher. I'm glad I'm not a math teacher. Okay, but if we do that, then our A's cancel out, and I'll write it up above. I'll write it down here. Then we get the final velocity divided by acceleration is equal to time, and that's totally what we're after. And I like the whole left to right thing, so I'm going to rearrange that if that's okay. I'm going to say time is equal to final velocity divided by acceleration. And by golly, I have the final velocity and I have the acceleration. So here we go. So time, T, is equal to 120 meters per second. Again, and I think I will go ahead and just do meters / seconds at the top. Divided by 9.8 meters per second squared. What I started to say, by golly, even if you don't do all of this other part, like breaking it down and rearranging, you have to include units in your problem. That'll be, remember the last part of your test is going to be like working problems, and they'll be worth like, I don't know, 3 points for a problem. And part of what I'm looking for is you put the units and kind of work it out. Your work's looking good, so keep looking. So let's see what can cancel. Now, time, so we're probably after seconds, right? Well, the way this works is the meters will cancel because they're in the numerator of the numerator and the numerator of the denominator. I don't know how does that work, but they do, they cancel. And similarly, one of these seconds will cancel out with one of those. So meters cancel, that seconds cancels out with one of these. So units that we're left with, I know it's kind of weird, but are what we call that. That's our units that we're after. Now, if you have a fraction in the denominator like this, you can bring it out at the denominator, or the bottom, if you flip it. That's the way I flip it. That's as mathy as I get. So actually, I can flip that, and that's like, what, S over 1, which is units of S. So let's see, our calculator is going to display something, and the display is, I'm sure you got it. I got 12.24489. So calc. 12.24489. All right, and units would be seconds, right? So now this is what I don't want you to like just do all those numbers. Okay, so this, and I'm not going to belabor it much, but as it turns out, this 0, although it's important, it's just a placeholder. It's kind of like those placeholders we did the other day for small numbers. So we don't count that, so we have 2 digits here, and of course we have 2 digits here. So I'm going to go with 2. So I'm going to go from left to right, so this is what, 12 seconds. So the answer is 12 seconds. That's it. One more. We're going to get through part 2. Yay. Okay. Here's a car. I'm going to draw a car. All right. Now, so this isn't a gravity thing, hopefully. We're dropping the car. The car is moving horizontally. Okay. So it's always moved. They always move from left to right for some reason. I'm just kidding. All right. So here's a car moving down the road. And it gives its acceleration is 5.41 meters per second per every second it goes. So 5.41 meters per second squared. Seems like that's quite an acceleration. Now remember, in these problems, this isn't like your normal driving down the road accelerating. We usually like accelerate for a second or two, then we let off and go at constant velocity. This is like you keep pushing down the accelerator, go faster, faster, faster. All right. So this is how long will it take? So let's see. Now I think I'll do a t is equal to question mark to be traveling a new velocity. So let's see. To be traveling, assuming it begins from rest. Okay, here's my other car. Or it's not, sorry, it's the same car later on, down the road, literally. Okay, so my final velocity is equal to 22.4 meters per second, and which is 50 miles per hour. And it starts, what's my initial velocity? 0. Perfect. My initial velocity is 0 meters per second. Cool. Makes it easy. If it is 0, then we can go ahead and use this one. The final velocity is equal to the acceleration times the time over which that acceleration occurs. So let's see. Looks like we need to rearrange for t. Does that sound right? So is this what we did last time? Or was it different? Divide by t. Divide by a. It is the same thing, isn't it? So this is a little bit ago we got We got t is equal to final velocity divided by acceleration. All right. So I'll do it down here. So time is equal to final velocity, which is 22.4 meters per second, divided by the acceleration, which was 5.41 meters per second squared. The calculator I get like a 4.14048, and it keeps going. So what would the units be? Seconds, yep. So, show of fingers, how many digits do you think I'm allowed? I'm thinking 3, yeah. So the way this works is I start from left to right, picking up my 3 digits. So that one looks pretty easy. So my answer is going to be, what, 4.14 seconds. Perfect. Time for coffee. Okay, so get this assignment down. So add this to what's due on Monday. On page 50, you need to do problem 16. So I did a few things different in the Canvas gradebook. So one of the things, like I told you, is now you have the ability to upload things. So if you're running late, don't have your problems done, you can still turn them in by midnight, the day that they're due, which is fine. But the other thing is I'm going to go ahead and instead of having each assignment be worth 10 points, basically whatever you hand in on that day is worth 10 points. So that made less assignments in that gradebook. That's really confusing. So some of those disappeared, so this is always one. All right. Have a great week. Skies are supposed to be clear. It's supposed to be warmer.